Pick up the nearest flat object you have, a book, a phone case, a plate. If you are in the kitchen, hold it flat and flick it into the air. Watch what it does. It doesn't just spin, it wobbles as it spins, a specific, graceful, rhythmic motion. That wobble is not random. It obeys an exact mathematical ratio. And in 1946, a burnt-out physicist eating lunch at Cornell noticed that ratio on a cafeteria plate and followed the mathematics wherever it led. It led to the Nobel Prize in physics. Quick myth fix. You may have heard Feynman wrote his PhD thesis on the spinning plate. He didn't. His 1942 thesis was on quantum mechanics, a different, equally extraordinary story. What the plate gave him was something rarer, the spark that reignited his entire career. That is the story we're telling. There are two questions in this video. First, why does a spinning plate stay airborne so beautifully while a spinning coin crashes so quickly? Second, how does a wobbling cafeteria plate connect to the behavior of subatomic particles and one of the most important theories in modern physics? The answer to both starts in a university cafeteria at the worst moment of Richard Feynman's life. By 1946, Richard Feynman was considered one of the most promising young physicists in America. He had spent the war years at Los Alamos working on the Manhattan Project, calculating, checking, solving problems under enormous pressure. He returned to academic life at Cornell as a professor, and almost immediately he fell apart. Not dramatically, not a breakdown anyone could easily name. He just stopped caring about physics. I was convinced that everything in physics was known. There was nothing interesting left to find out. I was dead. He sat in his office. He went to lectures. He tried to work. And the work felt hollow, because everything he did felt like obligation rather than discovery. The man who had spent years finding joy in pure intellectual play was now doing physics the way most people do jobs they've stopped believing in, showing up, going through the motions, producing nothing that excited him. At some point during that period, Feynman made a decision that sounds trivial and turned out to change the direction of theoretical physics. He decided to stop trying to do important physics and just play. No agenda, no ambition, no pressure to produce anything useful. If something seemed interesting, he would follow it. If it didn't lead anywhere, fine. It was in that state of deliberate consequence, free curiosity, that he walked into the Cornell cafeteria, and someone threw a plate in the air. The details of what exactly happened that day are slightly different depending on which account you read. But the core of the story Feynman told himself is consistent. Simone tossed a cafeteria plate into the air. As the plate spun and wobbled, Feynman noticed the red Cornell medallion on the rim of the plate, and he noticed something specific about its motion. The plate was wobbling, tilting as it rotated, and the medallion was rotating around the rim, but the wobble and the spin were not the same speed. Feynman's brain involuntarily did what Feynman's brain always did. It asked, why? Not in a formal way, not with any ambition. Just, that is interesting. What is the ratio between those two motions? And why is it that specific ratio? He went back to his office, not to do important physics just out of curiosity. For fun, because the question was there, and it annoyed him not to answer it. He worked out the mathematics. He found the ratio. The plate wobbles exactly twice for every single spin, a 2-to-1 ratio, precise, exact. Not approximate, forced by the physics of how mass is distributed in a flat disk. I went on to work out equations of wobbles. Then I thought about how electron orbits start to move in relativity. Then there is the Dirac equation in electrodynamics, and then quantum electrodynamics. It was like taking a cork out of a bottle. The plate led to the electron. The electron led to quantum electrodynamics. QED led to Stockholm. But before we get there, you need to understand why the plate does what it does. Because the physics is extraordinary in its own right. Put a coin on a table and spin it. Watch what happens over the next 10 to 30 seconds. At first it spins cleanly, nearly upright. Then it begins to lean. Then the leaning gets faster, more dramatic. The coin starts rattling, clattering, and then it slaps flat onto the surface with that distinctive staccato decelerating buzz. Typical spin time, 1030 SIAM behavior, rapid rattling collapse physics term. Euler's disked friction, precession. A coin has two properties that work against it. First, its mass is concentrated very close to its center. In physics, the relevant number here is called the moment of inertia, a measure of how hard it is to change an object's rotation. For a coin, because most of the mass is close to the spin axis, the moment of inertia around the spin axis is low. The coin doesn't resist changes to its spin very effectively. Second, a coin makes contact with the table on its thin edge. That contact point is directly below the coin's center of mass, right where all the weight is, as the coin slows down, because friction with the table and air resistance are constantly draining its energy. Gravity starts winning more and more of a battle it has been fighting the whole time. The coin's spin axis begins to tilt. The center of mass shifts away from the contact point, and now gravity is pulling the coin sideways as well as downward. This creates what is called precession. The coin doesn't fall over directly. Instead, its spin axis rotates around the vertical, like a top that is leaning and circling precession. Why it accelerates toward collapse as a coin slows. Precession rate increases, not decreases. The slower it spins, the faster it precesses. This is counterintuitive, but mathematically precise. Precession rate is inversely proportional to spin rate. The coin's final rattle is maximum speed precession in the moments before total collapse. The coin's low moment of inertia, its thin edge contact, and the inverse relationship between spin speed and precession rate combine to produce something almost theatrical. The slower the coin spins, the faster it wobbles. The faster it wobbles, the more energy it loses to the table, the more energy it loses, the slower it spins. A feedback loop, a death spiral. The coin accelerates toward its own collapse. A plate in the air has none of these problems. And the reason why is rooted in one key difference. Where the mass is, a plate is a disk, and a disk has most of its mass far from the center, spread out toward the rim. That single geometric fact gives a plate a dramatically different moment of inertia than a coin. Plate, mass at rim SUDI, high moment of inertia coin. Mass at center THUDI, low moment of inertia. When you spin an object with a high moment of inertia, it strongly resists any change to its spin axis. This is the same reason a bicycle is stable while moving and falls over when stopped. The spinning wheels have enough angular momentum to resist being tilted. A spinning plate, for the same reason, resists being tipped when it wobbles. When gravity and air pressure try to push the spin axis sideways, the plate's angular momentum pushes back, not by straightening out, but by precessing, rotating the spin axis in a slow, controlled, graceful arc. And here is the key difference from the coin. The plate is in the air. There is no table. There is no friction. The only forces acting on it are gravity and air resistance, without the table's friction constantly draining energy at the contact point. The plate's wobble stays stable for far longer. The coin is racing against friction that gets worse as it slows. The plate has no such enemy. Its wobble is gentle. Its spin is maintained. The air barely disturbs it, and the ratio between its wobble and its spin, that precise 2-to-1 ratio Feynman noticed, is what keeps the whole system coherent. Here is the mathematics that Feynman worked out in his office. When a flat disk, a plate, a frisbee, any flat circular object is thrown with spin and wobble together, something specific happens. The wobble rate is exactly twice the spin rate. Not approximately, not roughly, exactly twice. Why 2-to-1? The moment of inertia ratio for a flat disk, the moment of inertia around the spin axis. I spin is exactly half the moment of inertia around any axis through the center in the plane of the disk, E wobble. The equations of motion for a freely precessing body produce a wobble rate that is I spin 2. I wobble spin rate equals 1/2. Spin rate equals 1/2 spin rate, meaning the spin is half the wobble rate, or equivalently, the wobble is twice the spin rate. This ratio is entirely determined by geometry, not by the mass or size of the disk, for every full rotation of the plate about its spin axis. The wobble completes 2 full cycles. This ratio creates a kind of dynamic stability. The wobble and the spin are locked together in a fixed relationship, not fighting each other, but moving in coordinated harmony. The plate isn't struggling to stay level. It is doing something more elegant, using its own wobble to maintain its overall structure. When Feynman worked this out, just for fun, just because the cafeteria plate annoyed him, he wasn't thinking about Nobel Prizes. He was thinking about how beautiful it was that a flat disk in the air obeys such a precise, clean relationship. And then his mind, as it always did, started asking the next question. What else obeys this kind of relationship? What else has this exact structure of wobble and spin, of rotational motion coordinating with itself to produce stable, predictable behavior? The answer he began to suspect was electrons. This is the part most people who tell the plate story leave out, because the connection from cafeteria plate to Nobel Prize in physics is not obvious. It requires a step that Feynman himself described, and that step is about how he thought. Feynman's method of doing physics was almost always to find a physical picture, something he could visualize, something that had the right shape, and then write the mathematics that described that shape. The plate wobbling in a precise 2-to-1 ratio was a physical picture. Spin axis rotating around a fixed direction. Wobble rate locked to spin rate by geometry. The whole system moving through space carrying its own internal structure with it. That is exactly how a relativistic electron moves. An electron has spin, a quantum mechanical property that makes it behave like a tiny spinning object. When an electron moves relativistically, close to the speed of light, its spin axis precesses around its direction of motion. The mathematics of that precession has the same fundamental structure as the mathematics of Feynman's wobbling plate. Playing with the plate equations, Feynman started noticing echoes. The way the plate's angular momentum vector traced out a cone in space reminded him of the Dirac equation, which describes how relativistic electrons behave. He started playing with those equations the same way, not to solve a specific problem, but to see what the geometry looked like. And that play led to diagrams, simple visual representations of how particles interact by exchanging photons, Feynman diagrams. The visual shorthand that physicists worldwide still use today to calculate the outcomes of quantum interactions. The mathematical framework behind those diagrams, quantum electrodynamics, QED, is the most precisely tested theory in the history of science. Its predictions match experiment to better than 1 part in a billion. It was like taking a cork out of a bottle. Everything just poured out. A wobbling plate in a cafeteria uncorked the most successful physical theory ever written, because Feynman was playing. Because he wasn't trying to do important work. Because the question, why does the plate wobble twice as fast as it spins, had no consequences attached to it. The freedom was the method before the payoff. One quick clarification that the internet consistently gets wrong. Feynman's actual PhD thesis was titled The Principle of Least Action in Quantum Mechanics, submitted to Princeton in 1942. It laid out the foundational mathematics for the path integral formulation of quantum mechanics. This is separate from and predates the cafeteria plate story by 4 years. The plate happened at Cornell in 1946, after the war, during the burnout period. The two stories are often fused into one. They are not the same story. The PhD thesis was equally important, possibly more technically foundational, but it came from systematic effort, not spontaneous play. The plate story matters because of what it shows about how breakthroughs actually happen. Not from pressure, not from ambition, but from curiosity applied without consequence to a question that happens to connect to something deep. Feynman's PhD was an act of disciplined construction. The cafeteria plate was an act of play. Both were necessary. Both produced physics that changed the field. Here is what this video has actually been about. Yes, the physics, the 2-to-1 wobble-to-spin ratio. The moment of inertia of a flat disk, why coins die in a friction-driven feedback loop while plates fly in graceful coordinated arcs. All of that is real and precise and worth understanding. But the deeper thing is this: Richard Feynman, at the most stuck moment of his career, recovered not by working harder, but by giving himself permission to not care about the outcome. He didn't spin the plate because he thought it would lead somewhere. He spun the plate because someone threw it in the air, and it was interesting was enough. Physics disgusts me a little bit now, but I used to enjoy doing physics. Why did I enjoy it? I used to play with it. I used to do whatever I felt like doing. It didn't have to do with whether it was important for the development of nuclear physics, but whether it was interesting and amusing for me to play with. A spinning plate wobbles twice as fast as it spins because of a geometric ratio locked into flat disks by the mathematics of angular momentum. That ratio, noticed by a burnt-out physicist eating lunch and watching a plate in the air, became the thread that led him back to the work that earned him the Nobel Prize. The plate didn't matter, the curiosity did, the willingness to follow a question that had no business being important, and find out that it was. If you want to understand Feynman's actual path integral method, what the PhD thesis actually said, and why it became the foundation of modern quantum field theory, that video is next. Subscribe so it finds you. I'll see you in the next one.